Hi everyone, and welcome to my presentation. I am Roberto Ramos Chavez. I am a research engineer with Unified Streaming. In the following 15 minutes, I would like to present the testbed based on MPEG NBMP standard in the context of MMSys 2021 for the research track. The presented testbed integrates various components for reproducible experimentation of different distributed media processing workflows, or DMPWs. The testbed is capable to allocate, configure, and assess different types of media processing workflows in cloud environments. So let's go ahead and get started. But first, it's important to highlight some of the motivation of this work, specifically the investigation of the combined effects of DevOps and various deployment configurations of media streaming backend services. More often, we see a higher trend for over-the-top services and TV broadcasters to move from on-premises infrastructure to cloud providers. However, deploying of media streaming at a scale prevails challenging but not trivial task. So we need to be aware of many devices to support, different codecs to support, different type of content to support, but also the integration with third-party systems such as an encoder or content delivery networks. This has to be always ready and flexible for any type of these media processing functions. So what's a distributed media processing workflow, or DMPW? Most cloud providers offer three main components for deploying media services. One is computing power, storage, and an orchestrator to initialize and control some of these services. These three components are commonly deployed in a centralized fashion. However, most popular media workflows require the integration to other third-party services, such as a content delivery network or any other type of media processing function before delivering the media to multiple client devices. This is in the form of video adaptive streaming protocols such as MPEG- or HLS, to give an example. Another computing service example is edge computing, that provides lower latency levels to client devices by being geographically closer to the final user. The communication between edge nodes and the client devices can be through wired or wireless networks such as 5G. So, what's some of the most common media processing functions in media processing workloads? So, we could have an encoder A that generates different bitrate ladders of the content, and encoder B that provides redundancy and resilience to our workflow. In addition to other functions such as playlist generation, media repackaging, watermarking, ad insertion, or even digital rights management. Most of these services are working in a centralized cloud, but with edge computing we can move some of these media processing functions to the edge, such as digital rights management, ad insertion, and also watermarking, to give an example. DMPW comparison. Comparing DMPWs requires multiple and reproducible experimentations. The main objective of comparing DMPWs is to obtain the optimal workflow for our media streaming setup and always be ready to be more flexible, more resilient, more cost-effective at every point of the workflow. So we always have to measure. But what exactly do we need to measure, and what are the challenges for DMPW comparison? We have enlisted some of the challenges when comparing DMPWs that we consider of great importance. One, realistic load generation at a scale that should be made out of different machines to emulate a realistic load. Soak testing that should have the capability to test long period of time testing. Peaks that could be multiple users and joining a live stream unexpectedly. Different heuristics such as rate adaptation. Two, many different configurations such as edge deployment or software configuration. Three, different hardware that could be virtual machine types or the size of this virtual machine, such as the number of cores that we require and the memory. Four, different cloud computing technologies such as containers versus serverless or even hypervisor based. Five, different media processing functions such as video audio encoders, packagers for MPEG- to give an example, video transcoding, video encryption, etc. 6. The challenge of measuring all these thousands of metrics per server. And we saw also a 7 challenge, that is the lack of testing methodology for cloud media streaming workflows. And of course, this becomes too many permutations of variants. Paper contributions. In our paper, we provide 3 main contributions: MPEG NBMP testbed implementation based on the reference architecture with the following capabilities: automated orchestration and deployment of DMPWs, tools for workload generation at scale, tools for storage and visualization of results, standard-based workflow descriptors and APIs. Second, the evaluation of MPEG-HLS distributed streaming workflows with different experimental factors such as cloud instance type comparison, different object storage interconnect implementation comparison, media processing function task comparison, distributed edge deployment comparison. The third is a data-driven approach to assess new and updated DMPWs, using the experiment variance of mean metrics, and we added a classifier for failure and health detection in DMPWs. MPEG network-based media processing, or NBMP, has the objective of providing media processing that is carried out different points in the network through different media format specifications, workflow descriptors, and APIs. It uses a reference architecture for cloud processing of media. The targets are delivery of immersed media, real-time processing, and large-scale streaming. The standard itself was published in December 2020, and some of the companies involved developing this standard is Samsung, Tencent, Nokia, and SK Telecom, to say some of them. The following figure shows the NBMP testbed implementation. We have used 6 components from the reference architecture, that is the NBMP source, the workflow manager, the function repository, the media source, the media processing entity that contains the media processing function, and the media sync, that in this case it acts as the workload generator, generating requests to the media processing function. In addition, we have added 2 other components that for analysis, visualization, and export of all these real-time metrics. The following figures provide examples of the NBMP testbed UI. On the left side, we provide an example of some of the time series metrics using Grafana software. And on the right side, we provide a dashboard of workflows which provide important information regarding the state of the workflows. For example, the time the workflow was initialized, the configuration information of the workflow, if there was a failure during the configuration or the testing, and many more information for analysis of the workflow. So what are the example test cases of the DMPW that we'll present in this presentation? We will show some results based on cloud's instance type selection, function specific configuration, DMPW per task evaluation, DMPW edge deployment evaluation, and DMPW health and failure detection. The first use case evaluation, we have considered Amazon Web Service as a cloud provider to compare different types of cloud instance types. The table at the left side shows 4 different types of cloud instance families given by the cloud provider. First, the general purpose, compute optimized, memory optimized, and storage optimized. Each cloud instance family is recommended by the cloud provider based on the type of workload that our application requires. However, sometimes it's challenging to know which type of hardware is more suitable for each media processing function. So we have selected a couple of instances that provide different hardware specifications such as CPU type, clock speed, amount of memory RAM, network bandwidth, the cost of dollar per hour, and the type of hypervisor. In this specific case, we want to find out what is the best cloud instance type for just-in-time packager function, which creates a playlist generation, and media packaging for MPEG- and HLS. This is based on a remote media content located in an object storage. So we see some results about this DMPW comparison, we could find that in this case for this just-in-time packager, the cloud instance C5 family, which has an AMD processor, had the best results among all the cloud instance type compared, with the lower response time in this case. So based on previous slide, we have divided the 12 different type of tested cloud instance into two groups, with the objective to visualize and compare the cloud instances among the following metrics: lower CPU usage by the cloud instance, lower price of dollar per hour, lower latency of response time reported by the workload generator, higher throughput transferred towards the workflow generator, and the lowest memory consumption by the cloud instance. In this case, for this media processing function and workload generated, the cloud instance C5 large obtained the best results among all the other Testbed cloud instances. The second use case evaluation is based on function configuration. For this evaluation, we have considered the function configuration on software base. The first two configurations, A and B, we use the crawl software to request content from the media source, for the exception of B, that uses a backend cache proxy to cache byte range requests. The configuration C and D, we use Apache Web Server internal subrequests to request content from the media source. Based on certain metrics, we use the inter-experiment standard deviation of metrics mean to identify failures and high variations. Therefore, configuration D was the most suitable configuration for this media processing function, and configuration B provided incorrect configuration with a high inter-experiment standard deviation for metrics mean. Use case evaluation 3 is based on per task comparison, which provides an estimate of average response time of each of the media processing functions in our DMPW. Here we measure the average response time for packaging media segments, manifest generation, and encryption of media segments. Also, we use FFmpeg to translate two different type of media segments of 2 seconds and also 8 seconds, and identify if there's a high variation from the different target bit rates. The fourth use case evaluation is based on the edge deployment comparison for DMPWs. We have selected 3 different edge deployment configurations in 2 different cloud regions, A and B. Configuration A, in this case, the media store is located in region A, and the media processing function is located in region B, together with the workload emulator, which is in charge of requesting MPEG- and HLS media segments to the media processing function. Configuration 2, in this case we move the media processing function to the cloud region A, and we add a cache function layer in region B for media segment caching. Configuration 3, this last edge configuration, we move the media processing function and cache function to region B. In this comparison, we have assessed the average response time and the average request per second of the media segment requests. Surprisingly, the edge configuration, third edge configuration, provides the lower response time and higher request per second, with almost 10 times higher when compared to configuration 1. Fifth and last use case evaluation, we have selected a variational autoencoder algorithm to analyze the time series metrics at the server side. We use a trained variational autoencoder to reconstruct the time series to assess the error and decide if it contains a nullity or not in each experiment. The first part of the network tries to condensate the information from input X into a hidden layer H. The second layer does the opposite. For the hidden layer, it constructs something as similar as possible to the input X. We have optimized the autoencoder by minimizing the reconstruction error, doing some tuning parameter tuning, and finally we have labeling the experiment based on the number of client errors reported in the dataset. For example, if the case there are client errors occurrences, data instances are labeled as unhealthy or otherwise they are considered as healthy. In our paper, we provide three main contributions. 1. MPEG. So what are the next steps? We intend to use the testbed to compare DMPWs using other type of processors such as ARM-based. We also we intend to do a comparison of light setups with encoder synchronization. Additionally, the comparison of optimization for ad insertion and content stitching, and finally, the assessment of DMPWs with microservice architectures. If you have any questions, please feel free to ask. Thank you, and for any questions, feel free to contact me at roberto@unifystreaming.com. Thank you.